Here we have a map of the major deserts on the surface of the Earth, and I'd like you to take a few seconds and see if you can find a pattern in the way that they're distributed. So take a few seconds now. You may have noticed that they seem to be clustered near certain latitudes. They seem to be clustered around 30 degrees south latitude and 30 degrees north latitude, without many deserts near the equator. And so the question is, why? What's the reason for this? The explanation involves an atmospheric circulation pattern called Hadley cells. And so that's going to be the topic of today's video. What are Hadley cells? How do they form? How do they persist? And how do they give rise to this pattern that we see, where deserts are near 30 degrees north and 30 degrees south? And in order to understand Hadley cells, the big idea that we need to understand and keep in mind is this idea of differential heating. We know that the Earth is not heated evenly across its surface, and it turns out that this gives rise to certain atmospheric circulation patterns, namely Hadley cells. Another thing that we'll need to think about and keep in mind is that as air rises, it loses moisture. So as it rises, it cools, and the water vapor condenses, and then that falls as rain. So that's really important also. It's an important piece of this puzzle. So let's discuss this differential heating. So here I've got a representation of the Earth with 30 degrees north latitude, the equator, and 30 degrees south latitude. And in this orientation, for simplicity's sake, this is what it would look like during an equinox, so March 21st or September 21st. And these arrows represent sunlight or radiation from the sun. So we know that the Earth's surface is not heated evenly. That's why we have higher temperatures near the equator and in the tropics than at the poles. And this differential heating also affects the atmosphere in important ways. So let's zoom in on the equator, or region near the equator, and discuss how this differential heating affects the atmosphere. So I'm going to draw for you a couple of squares, and these squares will represent volumes or parcels of air. And a common theme that you'll notice when learning about or discussing weather or climate is that you'll often talk about volumes of air, properties of volumes of air, how they move on the Earth's surface, and how they interact with each other. Because this helps us to understand weather and climate patterns on a large scale. So we're going to do that here. So we've got these three volumes of air that we're going to think about, how they move and interact. So let's start with this middle one, near the equator. Well, since it's near the equator, it's going to be warmer than the surrounding air, than the air north and south of it. So we'll turn this red to represent it being warmer. That's because there's more sunlight falling per area, per unit area, more energy falling per unit area at the equator. And this energy will re-radiate as infrared, which is absorbed by the atmosphere. So we have warmer air here. And you might know that warm or hot air rises. So this volume of air will rise in exactly the same way that a hot air balloon rises. We have warmer air that's less dense than the surrounding air, and so the buoyant force will cause it to rise. Now, as this air rises, it cools, and I'll represent that by turning this blue. And as this air cools, the moisture, the water vapor inside of it, will condense and fall as rain. So I'll draw some ellipses here to show that rain is falling out of this. And at the equator, we get lots of rainfall. We have tropical rainforests there. Now, thinking about these parcels of air, these volumes of air, this air that rose left a vacancy, left a space here, and these volumes will move to fill in that space, like so. Now, back to this volume of air. What will it do next? Will it continue rising into space forever? Well, we know that's not what happens because the Earth has an atmosphere. It doesn't lose its atmosphere over time. And so we know that it must do something else. And everything that goes up must come down. But it can't go straight back down because this air filled in that space. from north and south. So this air will do something else. It will migrate north or migrate south first before descending, before going back closer to the surface. And it turns out that this air descends at around 30 degrees north latitude and 30 degrees south latitude. Now you might be wondering to yourself, why does it descend at that latitude instead of making its way all the way to the poles before descending and then going back? And the reason is that because the Earth is spinning, anything that's moving along its surface will be deflected by the Coriolis effect. And this is discussed in a separate video. But suffice it to say, these volumes and parcels of air, as they move north or south, they are deflected, and so they can't go all the way to the poles. They're deflected by this Coriolis effect. Alright, let's zoom back in on these parcels of air here. Let's think about what's happening to this volume of air now. I'll erase that rain. Well, this volume of air is now closer to the equator, so it's going to be warmer. And I'll turn it red to represent that. And warmer air rises, cools, the moisture condenses and falls as rain. And these volumes of air that descended are now going to fill in that space that was left. So now you've probably noticed that we're setting up a pattern. We're setting up a circulation pattern. And let's go ahead and draw this with lines to be clear about what it is. So we have air near the equator that's rising because it's warmer, migrating north, the northern hemisphere, before descending and then migrating back to the equator. Same in the southern hemisphere. We have warm air that's rising before migrating south and descending and then making its way back to the equator. So I'll also draw a few arrows to help us keep in mind the direction here. So we have the air going this way, back to the equator. So this pattern that we've just constructed, this pattern of atmospheric circulation is called Hadley cells. And I've just drawn a cross-section of Hadley cells here. But it's important to keep in mind that these Hadley cells, because the Earth is rotating, these Hadley cells go all the way around the globe. So you can kind of envision them in 3 dimensions like donuts. Donuts that encircle the globe and they're constantly rolling over themselves, churning up the atmosphere. So let's think about a few more volumes of air at the equator. So I'll draw a few more. So we need to keep in mind that at every point on the equator, because the air is warmer, we have hot air that's less dense than the surrounding air, and it's going to rise. So in this case, it'll come out of the screen towards you, and as it does, it will cool, and the cooling air, that will cause the moisture and water vapor inside of it to condense and fall as rain. And then these parcels of air will migrate north or south before descending at 30 degrees south or 30 degrees north. And this is happening all around the globe at the equator and the tropics. So we have these large-scale circulation patterns called Hadley cells. So let's think about what happens then if you're at 30 degrees north or 30 degrees south. Well, we've got this air that rose and cooled and lost its moisture. And because this is a constant pattern, because it's always rotating, always happening, you always have these descending masses of air from aloft coming down onto 30 degrees south latitude and 30 degrees north latitude. So this dry air is always descending from aloft. And this is what gives rise to this pattern that we see of the deserts being distributed at 30 degrees north and 30 degrees south. So we have Hadley cells that form through differential heating of the Earth's surface, and that heating causes the air near the equator to rise and lose its moisture, and then it migrates north or south and falls at 30 south and 30 north.